Thank you very much. I'm very grateful to the organizers for giving me the opportunity to give these 3 lectures on Alexander Efimov's beautiful new theory of algebraic K-theory. I really do think it's quite remarkable, and it even evokes sort of poetic feelings in me, which I tried to capture with this quote. So I'll leave it as an exercise to the audience to understand the correspondence between what Shakespeare wrote and what I'll explain today. Right, so, well, what is it about? Well, it's about kind of a broadening of the context in which algebraic K-theory can be defined. So maybe we can describe it in 2 steps. You know, at the very beginning of algebraic K-theory with the work of Grothendieck, it was originally based on vector bundles, say on a scheme. And this would be an example of an additive category or an exact category. But also in the work of Grothendieck, it was seen that one should actually expand this a bit and not look at vector bundles, but look at perfect complexes instead. And that's an example of a stable infinity category. And I'm going to put small here because it's important in these classical K-theory machines that you're feeding small categories into them so that it's well defined. And then we're going to expand it even more, and things like nuke x, which will be dualizable. But now these are large stable infinity categories. But what motivates this kind of expansion of the context in which K-theory is defined? Well, in my view, the goal is that we have K-theory, and we're always trying to, we have whatever kind of K-theory you like to think about. And the reason behind all of these expansions is that we want to make the input category match the K-theoretic behavior as much as possible. We're trying to make the categories approach the K-theory themselves, so that whatever you see on K-theory has a direct categorical explanation. So that you deduce everything in K-theory just by finding some functors between categories or whatever, and then just hitting it with K-theory. We saw a great example in Thomas's talk last week. But now I realize, looking out into the audience, that probably for most of you, life started here. You're all so young. You don't even remember what's a vector bundle. But maybe I'll actually start with a reminder of, so what was the motivation behind this expansion? Because it's actually quite similar, in some sense, the reasons why we make this expansion as well. So why this? And again, it goes back to the very beginnings of Grothendieck's study of algebraic K-theory. There was the Riemann-Roch problem, which Grothendieck relativized, an important part of his proof, and the crucial structure. So if f from x to y is a proper map of, say, smooth quasi-projective varieties, then we get a push-forward map on the level of K-theory of, say, vector bundles. Oops. But from the perspective of vector bundles, the construction is not so obvious. Let me remind you what you do. You take your vector bundle on X, that's fine. But then to get a well-defined thing, you have to take the derived push forward to Y. You get a bounded complex of finitely generated projective modules. Then you have to individually resolve those into vector bundles so that you can then define a K-theory class here. So it's kind of a little indirect from that perspective. But when you replace vector bundles by perfect complexes, you prove once and for all that it's the same thing under this hypothesis. And then on this level, you simply have the push forward functor. So this comes from, push forward functor on the level of perfect complexes. So just in one step then, once you set up K-theory in this context, you take a functor, a natural functor, it's just an adjoint to the obvious functor, and you hit it with K-theory, and you've got the thing that goes into the statement of the Riemann-Roch theorem. And this also lets you, you can also remove annoying hypotheses like quasi-projective if you work with perfect complexes. And this is related, so relatedly, so K-theory of perfect complexes always has descent, Zariski descent. And this is not clear for K-theory of vector bundles, except in cases when you can prove it agrees with K-theory of perfect complexes. So
it is even false, but I need non-separated thing to make it false, like gluing two copies of file A2 outside the origin, because there the vector bundle is the same as an A2, but you don't.
Yeah.
Okay, but it's not clear if you can.
Okay, so you're saying it's not just not clear, it's not true. Yeah? Yeah, okay, that's good. At least for non-separated things. Thanks. Okay, but then also once you've decided to make that expansion, then you get other things, you get other manifestations of this principle. So another thing is that, so then more examples of K-theory behavior coming from, being explained by category stuff. Well, here's a very simple one. Suspension on the category C induces -1 on K-theory. So in fact, once you decide to move to this setting, even what you might have thought was the most basic aspect of the definition of K-theory, namely that it's a group completion, that you formally adjoin inverses, you don't need to do that. The inverses are just automatically going to be there. So you can see the -1 on the category level as just coming from the shift functor. And just to give another simple example, for example, there's a so-called Bailenson full exceptional collection on P1, and that's what gives, in my opinion, the best explanation for why K-theory of P1 is the same thing as a direct sum of two copies of K-theory of a point. You just have a semi-orthogonal decomposition of the category into two things which are equivalent to the category over the point. Whereas from the perspective of vector bundles, it's a little less obvious how to see. And then another point is, well, every time you have one of these, you can make one of those by taking the bounded derived category, and it's a theorem of Gillet-Waldhausen that the K-theories are the same. So this is just a more general context. You can imagine that you can find stable infinity categories that don't arise from things over here, and now you have more things you can apply K-theory to, and that's nice as well. Okay? So what about this? Well, again, I can give two different sets of reasons. One is a motivation, so beforehand motivation of why this is not good enough. But then after you set up the theory, there's after the fact motivations where you can really see that you get a lot out of it, even neglecting your initial motivations. So let me start with, so why is K-theory of small stable infinity categories not good enough. So one example is, well, very similar to this actually. So, but if you want to do, say, Riemann-Roch or descent for K-theory, for algebraic K-theory, whatever this is, of analytic spaces. So not algebraic varieties anymore, but for example, formal schemes, rigid analytic varieties, complex analytic spaces. the K-theory of vector bundles or even the K-theory of perfect complexes doesn't work. It doesn't satisfy descent, for example, and the basic reason behind this is that in analytic geometry, your localization, restriction to open subsets are not actually localizations in the categorical sense. So you can't follow the usual Thomason-Turbo argument to establish descent. And then a second motivation, which is actually in some sense related, it comes from a beautiful story of Karoubi. So Karoubi said, he didn't quite prove it, I think it was proven later by Higson and maybe Suslin-Wodzicki, that if you take the algebraic K-theory, now I have to say what this means, but of the ring of compact operators on a separable Hilbert space, then this actually is topological K-theory. This is non-connective algebraic K-theory, and it gives you the full periodic topological K-theory spectrum. But, but what does this mean, K-theory of compact operators? Note that compact operators is a ring, an associative ring, but non-unital. So what the definition that's given for this is just you take the homotopy fiber of the K-theory of some unitalization, for example, the ring of all bounded operators on the Hilbert space, mapping to the quotient bounded operators mod compact operators. So it's some kind of relative K-theory. So you put this as an ideal in there, and you look at the fiber of this mapping to this, and then Suslin-Wodzicki showed that it's actually the same. This is their excision theorem in a special case, as any K of, say, R, going to K-theory of R mod compact operators, whenever K is a two-sided ideal in R.
Are you working with topological or algebraic K-theory?
I'm working with algebraic K-theory. Yes. And it's a theorem that it's homotopy invariant.
Okay, so you get KU.
Yes. Okay, that's fine, I guess, but where's the category?
And it is the non-connective K-theory?
That's correct. So this is in operator algebras and so on, people often talk about algebraic K-theory of rings, but they're kind of missing the categories, and the categories provide important flexibility. Okay.
So what's the relation between B and R?
B is an example of R. So B for me was bounded operators on the Hilbert space. So in Karoubi's exposition, he made that specific choice, but then Suslin-Wodzicki showed it actually doesn't matter which unital ring you embed your non-unital ring in, you always get the same answer.
So here one can define also topological K-theory, and it coincides with algebra.
That's correct. Okay, are there any other questions up to this point?
How does the right-hand side depend with H?
Well, H doesn't depend on H. Yeah, but H doesn't depend. There's only one isomorphism class.
Ah, okay, sorry.
Yeah. Yeah. Other questions?
And the automorphism group of H acts trivially
Yes.
in a homotopy sense.
Well, yeah. So don't worry, we'll give a much better way of thinking about all this in a second. So, or not in a second, at some point during the next few days.
What happens if you take a non-separable?
Oh, come on.
Okay.
I think you get the same answer, actually. Yeah. Yeah. Okay. All right. So we're going to be trying to move into this world of dualizable large stable infinity categories, but let me do it slowly. We have 3 days after all. So first, let me recall, I think it's already been discussed by Georg, how you can view these guys inside as large categories instead, at least up to idempotent completion.
When you say separate variable space, you forgot infinite dimensional.
You're right. You're right. I should have said infinite dimensional. Thank you. Yeah, absolutely. Yeah, that is crucial. Yeah, you're absolutely right. Okay, where? Oh, I guess. Well, okay. So recall, if you have I would say C0, a small stable infinity category, then you can produce a large one. So something in this ubiquitous category PRL. So it's a presentable, in fact, compactly generated stable infinity category. And you can pretty much go backwards. You can go backwards up to idempotent completion. So this, and if C0 is idempotent complete, then C0 is recovered as the compact objects. And the notation for compact objects is, I think you can put an aleph naught up there. So, because they're more properly aleph naught compact objects. In your definition of filtered colimit, it's finite diagrams that play a role, and finite things are the things that are smaller than aleph naught. That's why that notation is there. But that just means compact objects. And in fact, we want to do this we want to restrict to the idempotent complete world anyway, because that's the thing that makes that's the thing for which non-connective K-theory is always going to factor through the idempotent completion, and it's in that world that you have the best long exact sequences or fiber-cofiber sequences in algebraic K-theory. So we want to restrict to the idempotent complete context, and we want to pass to, when we're in the idempotent complete context, we want to pass to big categories anyway, because the only way you can ever establish a localization sequence in the small world is by passing to the big world and then looking at compact objects, or at least that's the only way I know how to do it. So it's kind of something you wanted to do anyway, but now we're going to be serious about it. And in fact, this gives an equivalence of categories.
So replacing a category with idempotent completion, does it change only K0? That is like for vector bundles, or does it change?
That's correct. It only changes K0. When you're talking about connective K-theory, yes, it only changes K0.
And the negatives are defined only for idempotent completion.
Right, or you could define them for an arbitrary one, but then you would define them as the non-connective K-theory of the idempotent completion. That's the only reasonable definition of non-connective K-theory for a non-idempotent complete guy is just idempotent complete and then take non-connective K-theory. But yeah, for connective K-theory, it only changes the K-naught. That's correct. So this gives an equivalence of infinity categories. So you have idempotent complete, small, stable infinity categories. People have all sorts of notations for these things. I'm just going to write it like this. And then exact functors, right? That's equivalent to compactly generated categories in PRL. But the morphisms aren't all morphisms in PRL. It's only the morphisms which preserve compact objects. So those are called the strongly continuous functors. And I'll make a little recollection about that just now. So,
stable, right?
Thank you very much, yes. Yeah. Yeah, so recall, Thomas went over this, but so recall f from C to D in PRL, so we're assuming already it commutes with colimits, is called strongly continuous. If the right adjoint, which automatically exists by some abstract adjoint functor theorem, also commutes with colimits. And if C and D happen to be compactly generated, that's just the same thing as saying that F sends compact objects to compact objects, so that you can actually sort of define the inverse functor here. Okay? But importantly, the definition makes sense for any. I didn't have to say compactly generated to make the definition I just gave there. So now, what are we going to do? So, or what does Efimov do? Now we'll expand, include more than just the compactly generated categories. And show that sort of K theory of the compact objects, so to speak. So this is in the compactly generated case. Well, naturally extends to these new categories. So if you want to say what K theory of a compactly generated category is, you just go by the inverse of that equivalence and take usual K theory. But now we're going to be talking about categories that aren't compactly generated, but magically you can still define K theory for them. Not by taking compact objects and taking usual K theory, but by, I don't know, magic. You'll see. Okay, so so the definition of the class of categories, this was given by Lurie. In SAG, page like 600 or something, I don't know. So for, but maybe I should say the one categorical analog. So I'm going to say the following are equivalent, and then I'll have a bunch of conditions. And for some subset of these conditions, the one categorical analog was investigated by Johnston and Joyal. So continuous categories, they called them. And there was an earlier study of continuous posets even before then. This is the infinity version. So for C in PRL, the following are equivalent. Now let me stress that in the statements of these I will be working in PRL, that is with continuous colimit preserving functors, not the category of where I only allow strongly continuous ones, okay? So the strongly continuous ones are very important. They will come into play, but not explicitly in this. All right? So the first is that C is a dualizable object in this PRL with its natural tensor product.
What is the unit?
The unit is spectra. I'm sorry, is the category of spectra. So. Spectra. But we'll see later exactly for which bases it doesn't matter. Whether, you know, when the absolute, there'll be a criterion later for when the absolute notion agrees with a relative notion. And then, so for example, if you're working over a ring, then you could equivalently work, you know, it'll give you the same definition if you work over a commutative ring instead. Yeah.
In that definition, should there be a history?
Yes, there should, thank you. And if I'm not going to ever consider any non-stable categories, so while I appreciate these remarks, let's drop them from now on. Okay, everything is stable.
For this, you don't need stability.
No, yeah. Correct. Okay, so, right, C is dualizable. The second one is that C is a retract of a compactly generated category. The third condition is maybe slightly more precise. So there exists a localization sequence. So where D and E are compactly generated. It's actually enough just to say D, and then E will automatically be compactly generated. And now here I want to stress that this notion of localization sequence is supposed to be the kind of thing that gives you a usual localization sequence when you pass to compact objects in the compactly generated case. So here I do want these to be strongly continuous. So I would maybe call this one I upper star and this one J lower shriek to give you an idea of what kind of functors these are. And the fourth condition is that if you look at ind of C, then that admits a functor. Now, okay, C is big, right? Let me just say this right now. C is big. But ind of C still makes sense, because you just adjoin all small filtered colimits to C. And it's still, it's not an extra big category, it's just a big category too. And there's a functor, but I guess you could call it realization, I don't know, which takes the formal in system to its actual colimit. This functor, the condition you want to say is that this functor has a left adjoint, which is called the, sorry guys, denoted y hat. So it's a version of the Yoneda embedding. So the right adjoint of this is the Yoneda embedding from C to in C. And now we're asking that this thing has a left adjoint, which will then automatically also be fully faithful. So it gives another way of embedding C into in C, which is non-trivial. So for example, in the compactly generated case, if C itself is an ind category of some small category, this takes that object of C and puts it inside ind of, it writes it as that ind object, where all the terms are compact objects in C, which is different from the Yoneda embedding, if you think about it. Okay. So let me sketch the proof, just to give an idea. Oh, maybe I'm supposed to go over here? Yeah. Or no, I'll do it here. So, right, proof sketch. So for 1 implies 2, so you use, so if D to E is a quotient, then so is C, or dual, let's say, C dual tensor D going to C dual tensor E, and then use the fact that every presentable category is a quotient of a compactly generated category, which you can actually take as the definition if you like. So then if you take this situation which exists for arbitrary C, and then apply this observation here, then by dualizability, this is equivalent to functors from C to D and functors from C to E, and you'll deduce that the identity functor here admits a lift, which makes C a retract of this situation here when C is dualizable. So then that's that. And 2 implies 1 is formal. If you've got an object with a categorical property, then any retract of it has the same categorical property. That's more or less the thing. And the same with 2 implies 4. You have to think a bit harder about to make sure it is formal, but it really is. You check it in the compactly generated case, and I basically already sketched the argument there. And then it passes to retracts. And 4 implies 3. 4 implies 3, you just take D equals in C. Well, or rather, a smaller version of C. So there's some presentability argument to say that in here you can replace C by some small subcategory for the purposes of this statement. And then you'll get a localization sequence like this, using the left adjoint as the inclusion, though this left adjoint is your J lower shriek. And then 4 implies 2 is obvious, or modulo the same business with cardinals and set theory and so on. And maybe we're done. What do we have? 1's equivalent to 2, 2 is equivalent to 4, 4 implies 3. Oh, we need that 3 implies something, but 3 definitely implies 2, yeah. Because already this thing and its right adjoint are exhibiting C as a retract of D in PRL. So let me make a remark.
So 3 implies 2.
Yes.
You have a localization sequence. What is the retraction?
Oh, you have, I said this should be strongly continuous, so it has a colimit preserving right adjoint, but it's also fully faithful. So the composition of this and its right adjoint is the identity.
Okay.
Yeah. Okay. So, right.
Continue this line of questioning.
Yes, please.
You said a retract in this category where all functors is required to be strongly continuous?
No. No. No, I made a very strong point at the beginning to say that the category I'm working in is just PRL for the purposes of this discussion.
So all functors are
just co-continuous or continuous or whatever colimit preserving functors.
And the right adjoint is colimit preserving.
No, I don't ask that. No. And in fact, I absolutely cannot ask that. So the only place where that was playing a role was in my definition of a localization sequence here. For the other statements, I'm really just working in the category where the morphisms are all colimit preserving functors, not just the strongly continuous ones. Now, very soon I'm going to pass to the subcategory, but for the purposes of this discussion, I had to work in this larger category. Okay. And it's important that, I'm glad you asked, because it is important to keep straight which category we're working in for a lot of this theory. Okay, so I make a remark. So these are all what you could call external characterizations. In the sense that they refer to not really to the category, if you usually think of a category as objects and morphisms, right? But this isn't what these characterizations are about. They're referring somehow to the place of the category within the world of all other categories. It's kind of, yeah. So there is also an important internal characterization using the notion of compact map. Which actually makes a lot of aspects of the theory much clearer, and we'll discuss that tomorrow. Okay? So then you can look at a category, and just by looking at the objects and the morphisms within that category, you'll be able to tell whether it's dualizable or not. You don't need to find it as a retract of something or whatever. Where are we? Yes.
Sorry. Is there external characterization being compactly generated?
No, I don't, yeah. No, not that I know of, yeah. Okay. Another remark. So I kind of sloughed over the sort of set theoretic technicalities with presentable infinity categories when I wanted to sometimes pretend like this was actually literally compactly generated, meaning into a small category. Now I'll make another remark. So if you investigate Lurie's proof that PRL has all limits, then in particular you see that any fiber product of compactly generated categories, and in particular any dualizable category, so CF3 above, is not compactly generated, i.e. Aleph not compactly generated, but Aleph 1 compactly generated. So we'll see this more explicitly tomorrow. It's actually somewhat important. So what is Aleph 1 compactly generated? If you're like me, you'd never really thought about it before looking into this theory. But a filtered colimit, again, is one where every finite diagram has a cone point, right? An Aleph 1 filtered colimit is one where every count has a stronger property. Every countable diagram has a cone point. And an Aleph 1 compact object is a weaker property than being a compact object. It says only that homming out of it commutes with Aleph 1 filtered colimits. And what it basically means is countably generated. If you think, or countably presented, if you think of compact as meaning finitely presented. So in a compactly generated category, the Aleph 1 compact objects will be the countable colimits of compact objects.
So the maps between the categories are percent compact, not necessarily. In PRL.
Yeah, I don't remember, but ours do, so I don't have to worry. Yeah. I don't remember, but the ones that I'm applying this remark to do preserve compact objects, so I don't have to remember. But yeah, one has to dig through Lurie to see.
What's the question?
The question was whether I said any fiber product of compactly generated categories is Aleph 1 compactly generated, and the question was whether the maps that you're taking fiber products along have to send compact objects to compact objects. The truth is I don't remember. But it doesn't matter for us because I was applying it here and here and to the zero functor here, and those all preserve compact objects.
For the so-called stable infinity, or more generally for presentable?
Yeah, stable doesn't matter there. Yeah.
So one can define what is compactly generated. Okay.
Yeah. Okay. Other questions?
But if you don't have stability, then sending compact object to compact objects is not as good as in stable cases.
Yeah. So we're going to see, I shouldn't have even mentioned this. We will see tomorrow that every dualizable category is Aleph 1 compactly generated. Okay? Let me say that instead. Forget I mentioned anything about Lurie. Okay. That was remarks. Yeah. And so that means, in fact, so in 4 you can, so it can replace 4 by 4 prime. You can make this an honestly compactly generated category. You can say that this colimit functor has a left adjoint. And then you're always in the presentable world.
So this is in addition that it is not obvious that Fourier equivalence of O prime without proving that.
Well, once you have this remark, it is obvious. Given this remark, it is obvious.
Without this remark, you can always put some cardinal, right?
Yeah, without this remark, you could always put some cardinal, but it's nice that you don't have to mess with that.
So why, if the real and adjoint, it goes to in C alpha 1 or?
Yeah, so I mean, there was part of the argument I sloughed over with how to go from this to this with a smaller guy. But if you're kappa compactly generated, then what Lurie shows in the proof is that you can, if you have this at this big level, then you always have it with the end of the kappa small objects instead. So it's some. Okay, I would rather, with respect to the question askers who are asking very legitimate questions, I don't want to answer any more questions about presentable cardinals and things like this. Okay. So more remarks. So now here's the definition. So these are going to be the objects in the category of categories we're looking at. They're called the dualizable categories. So we write. I forget what notation Thomas used, but I liked the look of it. I think it was PRLdual. So this is the infinity category whose objects are the dualizable, presentable, stable infinity categories, and the morphisms are now the strongly continuous functors. So things in six-functor formalisms that look like lower shriek or upper star, or lower shriek maybe along a smooth map or something, or upper star, they kind of count, but other ones don't. Okay, so thus, so small idempotent complete is a full subcategory of PRLdual via sending C naught to end of C naught. But the whole point is that this is not an equality. We're going to see a bunch of examples when I get to examples.
This morphism which preserve, something that preserve.
Okay, so we have a category. Let me list some categorical properties. So properties. So PRLdual ST. It's not a full subcategory, but it's a subcategory of PRL. We've thrown out some objects, but we've also thrown out some morphisms, right? Okay, but still. This commutes with colimits. And then I'll recall here, colimits in PRL are calculated by passing to right adjoints and taking limits. In just as infinity categories. So if you want to calculate a colimit here, you have a diagram of categories and strongly continuous functors. You just pass to the right adjoints and take the limit of that diagram of categories. That will automatically lie in here and will be the colimit. So that's one. Second is that PRLdual is closed under tensor product in PRL, and so are the morphisms, and we get a symmetric monoidal structure on PRST-dual. So if you take two strongly continuous morphisms and you tensor them together, the result is still strongly continuous. That has to do with the two categorical nature of the tensor product.
How do you see that it commutes with colimits? This embedding?
It's not that difficult. So if you use 1, then it reduces to the fact that tensor products commute with colimits, basically. Yeah.
So it not only commutes with colimit, but the colimit exists in the source also.
Yes,
in
yes,
general.
yes. Yeah, that's right. Exactly. Yes, that's right.
It reflects. I don't know. They have some notions.
Creates colimits. Yeah, exactly. Yeah, and yeah, I should have even said that. Yeah, and admits all colimits. Okay, and then the next property is that PRdual also admits all limits. These are more subtle. We'll discuss them tomorrow, once we have this notion of compact morphism. Yes?
I'm confused by the explanation you just gave. So
Yeah.
you said it follows from the fact that colimits commute with tensor products.
Yeah.
But certainly not in every symmetric monoidal category the dualizable objects are closed under colimit.
No, that's true, but it's a different category. We threw out some of the morphisms.
Ah.
Yeah, I invite you to think about it. I don't. Okay. Yeah. Okay. So where am I? Oh yeah. And so I just said PRdual ST has the tensor structure. This also admits all internal Homs. And these are, well, internal Homs are basically fancy limits, and these are also subtle. But subtle, by the way, means interesting. So you get really interesting new dualizable categories by taking even compactly generated ones and applying limits and internal Homs in this category. So subtle, i.e. beautiful and interesting. Yeah. Okay? And that's a key part of Efimov's theory, so don't think of it as just some technicality. Okay. Well, other closure properties. I'm sorry, I don't know. I kind of.
Presumably you don't have ambidexterity for space index diagrams anymore? Or is that still something that's true?
I have to remind myself what that means.
Like finite infinite products and coproducts in PRL or PRST are the same. For instance.
Yeah, I suppose that's not going to be true anymore. I can't say I've asked myself precisely that question, and I don't want to pause and do it now, but thanks, yeah. Okay. All right, so yeah. So suppose A, B, C is a localization sequence in PRLdual. Oh, did I put the L downstairs? Oh no, so I didn't put an L anywhere. Great, okay. So if, sorry, just, so now again I'll emphasize these are supposed to be strongly continuous. If B is dualizable, so are C and A. And big ol' warning, the converse fails. an example, do it to who else? The man himself. However, some things that you might want to prove using this fact actually are true. So, however, on the positive side, so if you have like C going to D, if we have what you could call an excision situation in the sense of Tama, so if you have this kind of situation, and these are localizations, strongly continuous, or we really only need this one to be, then if D, C prime, and well, D prime, I don't really need to mention it, but are dualizable, and this is a pullback in cat infinity, or in PRL, same thing, then so is C. So there's a fake proof of this using a false fact, which is that, okay, well, if this is a fiber square, then the fiber terms are the same. So, and then this will be dualizable because these are dualizable. So then this is dualizable and this is dualizable. This is an extension, so this is dualizable. That doesn't work. But instead, you can use some tricks from Georg's first article on excision, brilliant article, which kind of really, for me, started the whole thing. But I don't know if Sasha agrees, but probably. But so the proof sketch. So you embed C in this left tensor product, left fiber product construction. So then with the quotient given by D prime, you have a localization sequence like this. So it's enough to show that these left limits, or left pullbacks, or right pullbacks, or whatever, of dualizable are dualizable. Oh, I should say this should be strongly continuous too, sorry. And then you use, again, a result of Georg's, that ind of A cross over in B in C in complete generality. Oh no, I shouldn't use, well, A prime, A double prime is always the same as ind of the lax thing. And then this guy is dualizable, so it has this nice embedding into its ind category with via the new Yoneda embedding. And then you use that to see that this also embeds in its ind category via the new Yoneda embedding.
So it fails without lax.
Yes. Well, the general fact, yeah.
The end stuff commuting with fiber product is.
Yeah, that's right. Yeah. Okay. But with this trick and the fact that this is a localization, and this is important. So I should maybe, Andreichev. So I'll maybe mention some more things later on about analytic geometry, but this is important when you want to, say you have some construction for analytic spaces and you know on an affinoid that you get a dualizable category, then this kind of thing will tell you that you get a dualizable category on every quasi-compact open as well. So you can apply K-theory there in the sense of Efimov. So this is kind of an important gluing principle.
But I think I prove it differently. Yeah. So you can prove like that if the categories are compactly generated and the fibers are like compactly generated as well, then the fiber product is compactly generated. And then you just realize C is like retract. Yeah. It's not like true that like the fiber product of like the in category is like an in category, but it's still compactly generated. Okay.
Yeah. So it's okay. Yeah. I tried suggesting this argument to Peter twice, and he didn't. The fact that I had to tell him the second time means he didn't really try to check it. But yeah, I thought this should work, and but yeah. Anyway. Okay. Okay, so that's the category we're living in now, okay, these dualizable categories. Now what is the idea for extending K-theory to this larger setting? What time did I start?
2:30.
Ooh.
Yeah, 20 minutes.
Okay. I swear I could talk about this stuff forever. Okay. Darn, I wanted to give so many examples and arguments. Okay, so idea. So if C is dualizable, and then we choose a localization sequence where these are compactly generated, then we define what's called the continuous K-theory of C to be the fiber of the usual K-theory of the compact objects in D, mapping to compact objects in E. And I put it in quotation marks because, well, this isn't a definition, because I said you make an arbitrary choice and then. Now the first hint that this is a reasonable definition was Georg's very theorem on excision, which said that at least if there's a good reason why you have a relation between two presentations, namely that there's some pullback square here with D prime and E prime, then these fiber terms are bound to be the same. But Sasha came up with a better explanation. All apologies to you, Georg. Yeah, so the actual definition. So we used that actually there's a canonical such localization sequence, which we already saw in the proof of the equivalence of the definitions of dualizable. So use C going to end of Aleph1 compact objects in C, and then by definition, the quotient is called the Kalkin category of C. And it will automatically be compactly generated, being a quotient of a compactly generated category via a strongly continuous functor. Okay, so then we take this definition in that context, but note that K-theory of this category is actually equal to 0 by Eilenberg-Swindle. This category, Aleph1 compact objects, always has countable colimits. In particular, it has countable direct sums, which means that K-theory is bound to be trivial by Hilbert Hotel. Yeah? So that means that the real definition is that the continuous K-theory of C is equal to the desuspension, I guess you could say, of the K-theory of the compact objects in the Kalkin category. Okay, now this looks a bit crazy. Because what is this saying? It's saying now, I'm telling you now, if you want to understand K-theory, for example, if you want to understand K0, which is supposed to be the most, well, it's a lie, right? But K-theory is supposed to be the most accessible. That just means the definition is most accessible. Calculations can be crazy difficult of K0, as we know. Once you go above curves, and we might as well just shrug your shoulders and guess for a general variety. But you know, in principle, it's concrete. But now this is saying that K0 is not K0 anymore, it's K1. That's already not so good. K1 is harder to describe by generators and relations than K0. But even worse, it's K1 of some crazy category that we just built by taking a Verdier quotient with some infinite dimensional things and so on and so forth. Fortunately, that's not how you have to think about it. So let me now make a more abstract phrasing of the definition, which explains in some sense that there are more fluid calculational techniques available for coming to terms with it. It's still not easy, but So more precisely,
Sorry, I have a question.
yes,
Is this like going backwards from the Karoubi example? Like,
no.
we first go to like...
Mm-mm.
No, but let me finish. Like, you use the Colkin algebra to define K-theory and then show it's invariant, but here first it's invariant and then we use...
No, no, let me finish. Well, we have this inclusion that I mentioned before, small stable infinity categories, including into PR, why can I never remember? Okay, dual stable. Let's call this restriction, let's call this iota. Restriction along iota induces an equivalence of infinity categories. So you have the infinity category of all those functors from PRDual ST to we take and then take E a stable infinity category, presentable, say. It's not living in here, it's a target value for our invariance. So for K-theory, it will be spectra, okay? Think of spectra. Sending localization sequences to cofiber sequences, so that you have long exact sequences for localization sequences to functors from small stable infinity categories to E, sending localization sequences to cofiber sequences. And the inverse is implemented by so F goes to F cont, let's say. This very construction, you just plug in this small category with a shift. Moreover, F on the small level commutes with filtered colimits if and only if its continuous extension does. And this is the interesting direction. So you see, this is just a construction that proves existence, but it's a canonical, it's completely canonical thing. It's just the statement that you have an equivalence between two natural categories, and it doesn't matter how you write down the inverse. It really doesn't.
So the conditions imply that f of 0 is 0?
Yes. Wait.
Yeah, you have 0 in localization sequence.
Yeah. 0 goes to 0 goes to 0. Right. Yeah, I think they do. Thank you. It's good to think about, yeah.
But then you needed to know what to define a candidate phi cofiber sequence for. You need homotopy to the.
No. The space of null homotopies is contractible. The space of null homotopies is contractible. It's. On the left, yeah, not in E, but in the source, yeah.
So is there any abstract way to find maybe like a left or right adjoint of the function you wrote down without actually knowing like the formula?
No, I don't know, yeah. Yeah, it's interesting, yeah. You might think it's a right con extension. Maybe it is, yeah. But then it wouldn't be, then this fact wouldn't be so obvious, yeah. I don't know, but actually that fact follows. I don't have time to explain everything. I was going to sketch the proof. Well, the key point in the proof, which is really elementary, you can just check it. Oh, I'm out of time, aren't I? Oh no, I have 15 minutes or 10 minutes?
Yeah, 10 minutes.
Yeah, 10 minutes, okay. The key, let me just mention the key is that this Calkin construction which is, this key is basically all you need to know, sends localization sequences to localization sequences. And for this statement, don't be too naive. Calkin construction doesn't commute with filtered colimits. But if you don't try that, the next thing you try will work. Okay? Maybe I give, so we're interested in K-theory, but let me give an example where it's actually, the continuous extension is actually somewhat immediate. So let's consider, so E equals spectra, F equals THH, then F cont is the dimension of F cont of A as a dualizable object in PRL stable. What does that mean? So it's dualizable. What does that mean? It means you have, the unit is spectra. That means you have some A dual, and you have a co-evaluation, and you have an evaluation. And then you form spectra goes to A tensor A dual tensor A via co-unit, and then you contract here using the unit. And it goes back to, well, what am I doing? Did I do it right? So no, you just, it made it too complicated. Yeah, you just go back to spectra, you do this composition, so co-unit and unit. And then you get a co-limit preserving functor from spectra to spectra, and that's the same data as a spectrum, and that is THH continuous of A. And so if A is derived category of a ring, then A dual is just derived category of the opposite ring, and then you can check. This just gives usual THH of R. So now you see at least why this invariant very naturally extends to dualizable categories. But the point is every invariant does, including K-theory.
Justin, sorry, is it supposed to be obvious from this how to think easier about that?
About what? About this? Yes. Now the very first thing I said just works. Anytime you have write it as a fiber of a localization between compactly generated things, the K-theory of that thing is just a fiber of those K-theories. Meanwhile, this commutation with filtered colimits also gives you other tools to use for doing calculations. So basically, you can actually, from now on, you can completely forget about this formula. The formula just goes into the proof of this statement. This statement is all you need to do your calculations, and I'll give many examples.
Sorry, can I say again? So if I want to compute the left-hand side, what do I do?
Well, it depends on what C is. I can't give you a general procedure.
So can you repeat this again?
Yeah, the basic strategy with variations, for example, use of filtered colimits and so on. The basic strategy is just to write it as a kernel of a localization functor between compactly generated categories and take the usual K-theory of compact objects there, take the fiber. That's the basic strategy. Now, it gets more advanced, but that's how you start. Okay. I was going to give many examples of dualizable categories, and I still intend to. But it maybe means I won't get to as much analytic geometry at the end, but I think that's fine. We go at the pace we go. Maybe I have time to just discuss one example. Yeah. Well, let me make sure I didn't forget to say something important in this general discussion as well. Oh yeah, okay. Well, So first example. So let X be a, well, let's say a compact Hausdorff space, topological space. Then, if you look at the category of Sheaves of spectra on X, not hypersheaves, not Postnikov, whatever Sheaves, just Sheaves. This is dualizable. So the sketch of proof. So you can view Sheaves on X. You want to embed it into a compactly generated category, or as a retract. And the compactly generated category you choose is you embed it inside Sheaves on the site of compact subsets with the finitary topology. And there you're at finitary Grothendieck topology. So just finite unions of compacts give you covers. And that's compacts for very general site theoretic reasons. And the fact is that, well, this is strongly continuous, and the composition back is the identity. So Lurie actually explicitly describes this as a full subcategory of this, and from that you can deduce the desired claim. You can also see the dualizability, like the duality datum. It's also true that if you take Sheaves on X tensor Sheaves on Y, it's the same as Sheaves on X cross Y. And then you can see the duality datum just using geometric constructions with push forwards and so on. And then also Sheaves on, also dualizable for any dualizable D. And then there's a theorem of Efimov calculating the K theory of this dualizable category. So K theory of Sheaves on X with coefficients in D is the same thing as global sections of the constant sheaf on X with values the K theory of D. This was one of the magic things Thomas mentioned in his talk. This depends on the topology of X, so this really only depends on the homotopy type of X, or the shape of X. Quite a remarkable thing. So this is the first example of a calculation. And the proof doesn't even mention Culkin categories. So I'll sketch the proof, or a proof, I don't really know. Yeah. And then we'll stop, unless I'm already out of time, in which case I'll skip the proof. I have 3 minutes, it's enough. So proof sketch. So let's consider the left-hand side as a functor of X. So what do we have functoriality for? Strongly continuous functors. Okay? So if you have a map of compact Hausdorff spaces, the push-forward functor commutes with colimits because it's compact Hausdorff. That's one of the basic facts. So that means the pullback functor, which obviously commutes with colimits, has a colimit preserving right adjoint, the push-forward functor, which means we have functoriality in K theory. So this is a cohomology theory on compact Hausdorff spaces with values in spectra. And it has the following properties. So the first thing is that it sends filtered colimits, let's say preserves filtered colimits. Here, filtered colimits in the opposite category, so I'm talking about filtered inverse limits of compact Hausdorff spaces. And second, if K and L are contained in X, then this functor, call it F, and F of K union L is the same thing as F of K crossover F of K intersect L f of L. And this follows by an excision square. Oh, and this follows by filtering filtered colimits of categories. And then there's a result that the infinity category of all such f is equivalent to spectra via, in one direction, f goes to the value of f on a point, and in the other direction, like A goes to global sections of the constant sheaf on X with values in A. So it's kind of a weird version of Eilenberg-Steenrod or something for compact Hausdorff spaces.
Right, so A1 invariant somehow automatically.
Where are we?
Homotopy invariant somehow automatically follows.
What?
Homotopy invariant somehow automatically follows from this?
Yes. So yeah, it's not really a calculation in some sense. Yeah, I mean, I don't know. Yeah.
So when you take gamma XA,
Yeah.
in this sense, is it gamma in the sense of hypercom?
No.
It doesn't satisfy. Okay. It satisfies.
Okay, thank you for attention. Tomorrow I'll continue with more examples and this internal characterization and so on.
Any further questions for Dustin?
I don't know. Sorry. Just in case, Ofer. Okay.
So in this case, like is gamma x comma a just limit of a over x.
I'm sorry?
So I was just wondering what is gamma x comma a mean? Is it just a limit of a over x?
No, X is a topological space. And I look at the category of sheaves of spectra on that topological space. And I take the constant sheaf with values A and I take global sections.
No, but it's the same as the limit of the group point. X is the group point.
No, X is an arbitrary compact Hausdorff space. What you said doesn't make sense. I mean, if X is a finite CW complex, it is, yes. Yeah. No, make no mistake, yeah.
So this also give a topological field theory, something similar to this.
No, but I'll say something about topological field. No, I'll say something about non-topological field theories later.
What's an example of a subtle Hom in PRLdual?
Come back tomorrow. Uh-oh, okay. You've been nodding so pleasantly the entire lecture, so I chose you first.
Right, so there's this characterization of the dualizable object as retracts of compactly generated ones, right?
Right.
But that's in the category with more morphisms than we want. Right.
That's correct. That's correct.
But is there still some way of saying that like PRST-dual is like an item completion of small stable infinity?
No, the best I think I can say is this characterization in terms of kernels of localization functors. Yeah, and I don't quite know if it makes sense for an infinity 2 category, but I don't quite know yeah.
Is there a description of this K-theory in the case of longer compact Hausdorff space?
Yes, there is. Yeah, you just put, it's fun. You just put compact supported here. Where am I? Yeah, and you can see it by just compactifying and looking at the obvious localization sequence you get there.
Oh, I see. Okay.
Yeah. But it's fun to think about. So yeah, so the application is that so Kn of D is the same thing as K0. It's a looping of K theory or something. Sheaves on Euclidean space with values in D. Very fun. Yeah, exactly. Locally compact Hausdorff. Yes. Oh, we're in France, so just locally compact. Yeah. Yes.
Okay, so this theorem of Efimov, so is it saying something like the non-commutative motives PRLdual is the same as the non-commutative motives?
Correct.
So why didn't you mention that PRLdual is presentable? Or it's not?
I think Maxime Ramsey proved that it is. Yes. And I didn't mention it because I didn't go to his lecture where he talked about it, and also I prefer to calculate my limits directly to actually give a formula for them. So I'll be using that approach instead. Yeah.
If there's nothing further, let's thank Dustin again and resume at 5:30.